Hey, astronomy students, let's talk about how to find the distance above the surface of the Earth for a satellite in orbit around the Earth. So we've got a problem here. A satellite moves in a circular orbit around the Earth at a speed of 5.5 kilometers per second. Determine the altitude above the surface of the Earth, assuming that it's a sphere with a known radius and a known mass. And they gave us the universal constant for gravitation. So just as we typically do, let's do it down here. No, let's do it up here. I'm going to draw a diagram. So, nope, that's a pretty bad circle. So I'm going to try again. Here's the Earth. That's what I was trying to do. And then I realize this isn't a perfect circle by any means. Here's Earth. Look. Here's all the continents. And here's our satellite. And the satellite at that point has a certain speed v, and it's a certain distance r above the center of the Earth, but it's only a smaller distance there, altitude, above the surface of the Earth. You can't read that. This is the altitude. That's a little bit better anyway. So how do we do that? First, I want to remind you that Newton figured out that the universal law of gravitation says if you know the two masses and the distance between them, you can figure out how hard one is pulling on the other. So let's just quickly, the force due to gravity is equal to capital G m Earth, m satellite, that's an E, satellite, divided by the distance above the center of the Earth squared. And I'm going to call that, well, let's call it big R squared. So just as a reminder, this is the mass of the Earth, which is clearly a much larger number. So this first M is mass of the Earth. This is the mass of the satellite, which is much, much smaller. It's the kind of numbers you would typically associate with like maybe a small car. So they clearly are unbelievably different masses, but Newton's laws say that when the Earth pulls on the satellite's pulling on the Earth, and that's actually what this equation is trying to remind you of. By the way, I drew the little arrow on top, which is a very physicsy way of saying this, but anytime an object is being pulled, you need to know a direction. So for our satellite, it's actually being pulled towards the center of the Earth right there. So I don't really want to bother putting any sort of vector notation, but this is toward center of Earth. Always. So that it does not matter where the satellite is in its orbit, which I've drawn here. Anywhere it is, I suppose if I were, well, anywhere it is, this is the force between the two. By the way, one of the ways we could indicate that it's toward the center of the Earth, if we want to kind of be very specific, we could just say negative, because you know it's going down. So that's kind of a shorthand for the vector part of always towards the center of the Earth. So let's think about another thing that's important here. Anytime an object is moving in a circle, then the force on it is the mass of that thing, the mass of the satellite, times the centripetal acceleration, which is the mass of the satellite times the speed of the satellite squared over its radius in the circle. So this equation right here, this is the centripetal force equation. Centripetal. Anytime something is moving in a circle, you can write down its force as m satellite v squared over r. You can just do that. You're allowed to totally do that. And there's a lot of reasons why, but let's not get into that physics. If you don't believe me, you could always find proof somewhere that this is true. Well, let's actually take the two forces and set them equal to each other. This one says anything moving in a circle is mv squared over r. This one says that anything that has mass is being pulled on by this amount, and the negative is the direction, by the way. So the only reason I put the negative in there is to tell you that it's down. This mv squared over r is also always towards center. That's literally what centripetal means. Always towards the center. So this guy and this guy, they're actually pointing at one another. They're actually the same force. So I don't need the negative sign like I put in here to describe it for a vector, because I know that mv squared over r is towards the center, and I know that gravity is towards the center. So I can actually set them equal to each other. So that's g, mass of the Earth, mass of the satellite, over the radius of the orbit squared. That's what this big R, this, not the altitude, but the big R, is how far the satellite is from the center of the Earth. That's not what they asked, though. So we got to be careful. They're asking us for the altitude. I've lost that. They're asking us for the altitude, which is going to be the altitude, let's call it A, is going to be the radius of the orbit minus the radius of the Earth. So we have to account for this at the end. But we're not going to do that yet. Let's keep going. So over here, we just put the force due to gravity. This is how hard the Earth is pulling on the satellite. G m over r squared. And we're setting that equal to the centripetal force equation, which is the mass of the satellite, the speed of the satellite squared, over the radius of the satellite's orbit. And this, by the way, is extremely common for problems with orbits. Force from gravity equals centripetal force, and you can solve things. So notice the mass of the satellite cancels, and I'm going to draw a little arrow here to indicate I'm about to do some one of the radiuses or radii, one of the radii cancels, and so I'm left with big G mass of the Earth. By the way, that's a pretty important pair of things to be grouped together. Divided by the radius of the orbit equals now just the velocity squared. And by the way, this is the speed. So any satellite going a particular speed, here they told us the speed, it's going to essentially be going the same speed at all times, even though it's moving in a circle. So you could say it's accelerating because it's moving in a circle, but the speed never actually changes. So this thing right here is almost useful. In fact, what I typically do is I call this the orbital equation, v squared times r. So the universal gravitational constant, g, which is given in the problem, this tiny little number here, times the mass of the Earth, which is given in the problem in kilograms, that's there, that actually equals the speed of whatever it is orbiting, squared, times the orbital radius. So you could think of this as this guy right here is orbital speed, and this is orbit radius. So you'll notice that on the astronomy equation page, I've got little O's for orbit right there. So that's actually what we need to solve this problem, but we can't forget about this annoying thing up here at the top. Okay, so let's use some of our values here. Hang on, what are we looking for again, y'all? Let's be sure we know. We're looking for the altitude, but in order to find the altitude, we first have to find r. So really what we're looking for is the orbital radius. That's the unknown. So I'm going to scroll a little bit and give us some room. And let's take this over here. Big G times mass of the Earth. These are both known. My M looks a little upsetting, so I'm going to try that again. Mass of the Earth, that's better. Notice the mass of the satellite is not important. So I know that's a little weird and I kind of skipped over it. Let me say it again. The mass of the thing doing the orbiting actually is not important. Mainly that's because the Earth is so big. There'll always be one really big thing in the middle, and whatever's doing the orbiting is so small that this relationship is going to hold, so the mass actually cancels out on both sides anyway. And again, the trick here is that the Earth's mass is so large that it allows the satellite to move in a circular orbit, which is why we're allowed to use mv squared over r. So this is the centripetal force equation, this is Newton's universal law of gravitation, and then this thing right here is the orbital equation. And then I'm dividing by v squared. Hang on, let's fix that a little bit. I was going to divide by r, but we don't know r. So we're going to divide by v squared. We're looking for r. So that's almost the answer, okay? So what we're going to do is multiply the universal law of gravitation, the universal constant of gravitation times the mass of the Earth in the right units, divided by the velocity in the right units, and that will give us the radius in the right units. So just to point something out here, the velocity is given in kilometers per second. The answer is supposed to be in kilometers per second, but the universal law of gravitation constant that I mentioned before, it actually has to have newtons, which is meters per second squared, meters, and kilograms. So we have to be careful when we're doing that. So let's bring up let's go to Desmos, where we can actually solve this problem and see if we can't. Let's open that guy real quick. And let's put in our constant, so that's 6.67 times 10 to the negative 11. And that was big G. And then M sub E for Earth, the mass of the Earth. Let's go back and look. I've forgotten already. 5.98 times 10 to the 24th. So 5.98 times, I misspelled times 10 to the 24th. Confirm that. Yep. So there's big G and big M. And then they also told us the radius of the Earth in kilometers, which we need to fix, and the speed in kilometers per second, which we need to fix. So let's put, well, we'll go ahead and put V here, and that's 5.5, but that's in kilometers per second. So what we need to do is multiply by the number of meters in a kilometer, which is 1,000. 1,000 meters per kilometer. So that's 5,500 meters per second. That's pretty fast. And then R sub E for Earth, and I forgot that number already, 6370. 6370, but that's in kilometers. So we have to multiply by the number of meters, and the number of meters, which is 1,000, in a kilometer. So that's what I've done there. And you could multiply by 10 to the 3 there. Times. You could multiply by 10 to the 3, but this is me being explicit. I know there are 1,000 meters in a kilometer. So kilometers here, they cancel. Kilometers here, they cancel. Just reminding you of the typical way we solve these problems. We cancel out the units. We want meters on top. Okay, so I've got all the parts we need in my equation now. Let's scroll back down here. The radius, not the altitude. The radius is big G, big G, mass of the Earth divided by speed squared. So the radius that we're looking for here, the orbital radius, will equal big G times M sub E divided by the velocity, the speed or velocity squared. And so we can confirm here that these are in MKS units, meters, kilograms, seconds. This is in kilograms already, so it's good. This is now in meters per second. This is in meters. So this really giant number here, that's the actual answer, but we're looking for the altitude, which equals the orbital radius minus the radius of the, I misspelled E, the radius of the Earth. And if I look back, that's what they're looking for here. They want the altitude, the radius of the orbit minus the radius of the Earth. But then it says answer in kilometers. So we actually need to, after all of that nonsense, just to make sure the constant would work, we need to multiply by how many, 1 over 1,000 there. We want to multiply by how many meters or in a kilometer, but notice the kilometers need to be on top. This is now meters cancel. I'm left with kilometers on top. So it looks to me like the answer is the altitude is 6,815 kilometers. Hey everybody, I had to pause the video because I made an error. I had put 6.67 times 10 to the negative 11th, and I remembered as I was typing the numbers that the software we use, the website we use for UT homework, is the Quest website. It's very specific. So luckily I remembered before I saved the video and uploaded it. So I put G is exactly what it is in the problem, 6.67259 times 10 to the negative 11. So I put the entire value in there. The mass of the Earth, let's just confirm that's right while we're here. Yep. And then, I was trying one of the other versions, but the one we have right here says 5.5. And then radius of the Earth. Let's just make sure all of them are right while we're doing this. 6370. Okay, so there's G from the problem. There's mass of the Earth from the problem. There's our velocity from the problem. There's the radius of the Earth from the problem. There's the equation from our algebra. Then I subtracted from our orbital radius the the size of the Earth, the radius of the Earth. And then I multiplied by the number of kilometers in a meter, which is 1 divided by 1,000. So remember, I have this set of parentheses would be meters, and meters is in the denominator. I wanted them to cancel, so I'm left with kilometers on top. And the right answer is 6820.77295. You can type them all in there if you want. And that's in kilometers. That is an application of gravity mixed with centripetal force, so we can find the orbital equation, so we can find the altitude above the surface of the Earth for a satellite in a circular orbit. Okay, good luck.